A supernova is one of the most energetic and spectacular events in the universe, marking the explosive death of a star. These cosmic phenomena have intrigued scientists and astronomers for centuries due to their dramatic nature and their role in shaping the cosmos. Supernovae are not only visually stunning but also scientifically significant, as they play a critical role in the life cycle of stars, the creation of elements, and the evolution of galaxies. A supernova occurs when a star reaches the end of its life cycle, leading to a colossal explosion. The brightness of a supernova can briefly outshine an entire galaxy, emitting as much energy in a few days as the sun will produce over its entire lifetime. These explosions are a key part of the cosmic ecosystem, dispersing elements into space and triggering the formation of new stars. There are two primary types of supernovae, Type 1 and Type 2. These classifications are based on the presence or absence of hydrogen in their spectra and the mechanisms that trigger the explosion. Type 1 supernovae lack hydrogen lines in their spectra. They are further divided into subcategories such as Type Ia, Ib, and Ik, depending on the specific elements detected. Type Ia supernovae are particularly important because they occur in binary star systems. One of the stars is a white dwarf, which accretes material from its companion star until it reaches a critical mass and explodes. These supernovae serve as standard candles for measuring cosmic distances due to their consistent brightness. Type 2 supernovae exhibit hydrogen lines in their spectra. They result from the collapse of massive stars, at least 8 times the mass of the Sun, that have exhausted their nuclear fuel. The core collapses under its own gravity, leading to a violent explosion that ejects the star's outer layers into space. To understand supernovae, it is essential to examine the life cycle of stars. Stars are born in nebulae, vast clouds of gas and dust. Over time, gravity pulls these particles together, forming a protostar. As the core of the protostar becomes denser and hotter, nuclear fusion ignites, creating a main sequence star. The duration of this phase depends on the star's mass. Low-mass stars, including the Sun, evolve into red giants and eventually shed their outer layers, forming planetary nebulae. The remaining core becomes a white dwarf, which may later participate in a Type Ia supernova if part of a binary system. High-mass stars undergo successive stages of fusion, creating heavier elements like carbon, oxygen, and silicon. When the core fuses iron, energy production halts, as iron fusion consumes energy instead of releasing it. This leads to core collapse and a Type 2 supernova. A supernova is a complex interplay of physics, involving gravitational collapse, nuclear reactions, and shock waves. In a Type 2 supernova, the core collapse triggers the following sequence of events. When the core's mass exceeds the Chandrasekhar limit, approximately 1.4 times the Sun's mass, gravity overwhelms electron degeneracy pressure, causing the core to collapse into a neutron star or black hole. The collapsing core rebounds off the dense neutron star, creating a shock wave that propagates outward. The shock wave, combined with neutrino interactions, ejects the star's outer layers into space, producing the supernova's luminous display. Supernovae have been observed throughout human history. Ancient records from Chinese, Arabic, and European civilizations document supernovae visible to the naked eye. The most famous historical supernovae include SN 1054, recorded by Chinese astronomers, which created the Crab Nebula, and SN 1572 and SN 1604, observed by Tycho Brahe and Johannes Kepler, which were key in advancing the study of astronomy. Modern observations utilize telescopes across the electromagnetic spectrum, from radio waves to gamma rays. Instruments like the Hubble Space Telescope and ground-based observatories have captured detailed images of supernovae and their remnants. Supernovae are not just spectacular phenomena, they are also crucial to the universe's evolution. Their impacts include element formation, as supernovae are responsible for creating elements heavier than iron through a process called nucleosynthesis. Elements like gold, uranium, and iodine are dispersed into space, enriching the interstellar medium. The shock waves from supernovae compress nearby gas clouds, triggering the formation of new stars. Type Ia supernovae serve as reliable standard candles for determining the distances to faraway galaxies, aiding in the study of the universe's expansion. Supernovae influence the structure and composition of galaxies by redistributing elements and energy. The aftermath of a supernova is a region of space filled with the ejected material known as a supernova remnant. These remnants, such as the Crab Nebula, are often stunningly beautiful and scientifically valuable. They emit radiation across the electromagnetic spectrum, providing insights into the explosion's mechanics and the composition of the expelled material. The remnants of a supernova's core can form exotic objects like neutron stars or black holes. Neutron stars are incredibly dense objects composed primarily of neutrons. A neutron star's mass is similar to the Sun's, but compressed into a sphere just a few kilometers in diameter. If the core's mass is sufficiently high, it collapses further to form a black hole, a region of space with gravity so intense that not even light can escape. Advances in technology and observational techniques continue to enhance our understanding of supernovae. Projects like the Vera C. Rubin Observatory aim to detect thousands of supernovae each year, expanding our knowledge of these phenomena. Additionally, gravitational wave detectors, such as LIGO and Virgo, may provide new insights into the role of supernovae in the production of gravitational waves. Supernovae are among the universe's most fascinating and impactful events. They illuminate the cosmos with their brilliance, enrich the interstellar medium with essential elements, and drive the evolution of galaxies. Studying supernovae not only deepens our understanding of stellar life cycles, but also sheds light on the fundamental processes that shape the universe. As technology advances, the mysteries of these stellar explosions will continue to unravel, revealing even more about the dynamic nature of the cosmos.